Topic 3.10 is about solving trigonometric equations and inequalities. We're going to focus mainly on equations today, but the ideas of inequalities follow suit from what you know from what we're going to learn today and what you already know about inequalities. I have this sine function graph for you here, and my question for you is, what would be the solution to the question if I posed sine of some angle is equal to 1/2? That means I want an output to be 1/2, and I want to know what inputs would give me the output of 1/2. Well, here's 1/2 as an output. Where does this graph cross this 1/2 line? At pi over 6. I heard somebody else say at 5 pi over 6. I don't know why this is not circling. Does anybody else see some more places where it might be a solution?
I can't see what that is. Is that 2 pi?
17 pi over 6.
13 pi over 6, 17 pi over 6. And then, clearly my graph is going to keep going, right?
Yeah.
How many more solutions to this question would there be?
How would I know?
I'm so glad you said that. How would I know is what she says. There's an infinite number of solutions to every trigonometric equation. Because the domain of these functions goes from negative infinity to infinity and the graph bounces back and forth between -1 and 1, there's an infinite number of times that you'll get an output that's in the range of the function. So when we are solving equations that are trigonometric equations, we are going to have to write what are called general solutions to a trigonometric equation, meaning you're not just giving me x equal to pi over 6 or x equal to 5 pi over 6. You're going to have to give me an equation that tells me all of the solutions to this trig function. For the graph that's written up here, you guys answered and found 4 of the places where sine was equal to 1/2, and it would keep going. So instead of writing them out from negative infinity to infinity, because you'd literally be here for your entire lifetime doing that, what we would write is that sine of something is equal to 1/2 when that something is pi over 6 and every revolution after that of pi over 6. So here's pi over 6. If I add 2 pi, I get here. If I add 2 pi, I get to the next solution. I also have a second solution at 5 pi over 6 and every revolution afterwards. Here's 5 pi over 6, add 2 pi to that, add 2 pi to that, on and on. Now, let's break down what this sort of looks like. This part right here, this 2 pi, how is 2 pi related to sine?
What do you mean?
Where else have we answered 2 pi as the answer to something?
As the over something.
Let me feed it to you. What is the period of sine? 2 pi. What's the period of cosine? 2 pi. And then we learned recently that the period of tangent is not 2 pi. What is the period of tangent? Just regular pi. So notice that as we're writing the general solution for sine, we will put plus 2 pi k, given pi is an integer, for every equation for sine. We will also say the same thing for cosine, plus 2 pi k, because 2 pi is the period. And so every time this function repeats itself through its period, it's going to have another solution that mirrors that one. But when we get to tangent, notice that tangent is simply just pi because the period of tangent is just pi. We only need one solution to the pi equations instead of 2 like sine and cosine. And we'll see some examples of that later. It has everything to do with the values around your unit circle. So today is going to be a little bit of an old-fashioned algebra solving day mixed in with trigonometry. Our end goal of the day is to be able to take a trigonometric equation and solve it using algebra skills. The steps are as follows. Number 1, you're going to isolate a single trigonometric function on one side of the equation, which may require factoring. Meaning, I want the equation to say sine of x equals, cosine of x equals, tangent of x equals. I don't want it to say sine squared of x equals or 5 sine of x equals. I want it to just say the trig equation itself. Then you're going to find the corresponding angle measure on the unit circle that satisfies the given equation. We're going to have to think what input values would give me that output value. Then you'll consider any domain restrictions on the problem. And when I'm talking about domain restrictions, I'm not talking about the inverse trigonometric ones like when we folded our unit circle last class. Not those. I'm talking about the problem itself saying I only want answers between 0 and pi, or I only want answers between 0 and 2 pi, because that means we don't have to write a general equation. And once we identify those domain restrictions, we will either write down the solutions or the general equations, general solutions for each of those problems. Are you ready to see what one looks like?
Yeah.
Great. The first question says, what are the values of theta where 6 times sine of theta is equal to 3 times square root 2? Okay, so first things first, let's just write down our equation nice and fresh so we can have it ready to go. Our first goal is to isolate the trigonometric equation. The function. What is the trig function we have in this problem? Sine. What is in front of sine right now? How do you get that to go away? Divide it. So on both sides, I'm going to divide by 6. And when I divide by 6 on both sides, the 6 in front of the sine is going to cancel out. So all I have left is sine of theta. Check. That's what we wanted. And I just need to simplify 3 square root 2 over 6. Ignore the square root 2 for a second. And if this just says 3 over 6, what does that reduce to? 1/2. The 2 but in the denominator. So this becomes square root 2 over 2. Our spidey senses should be going off, right? What are the values of theta? What angles give me square root 2 over 2 for sine? Pi over 4. Okay, I'm so glad we said that. Is that the only place? Hello, pi over 4. Is that the only place where sine is going to be equal to positive square root 2 over 2? Isn't there another quadrant where sine is positive?
Can we look at our...
I would like for it to come from your brain today. That would be in quadrant 4. Is sine positive in quadrant 4?
It would be in the one next to it.
It would be in the second quadrant right next to it. What is the version of pi over 4 in quadrant 2?
2 pi? Oh, wait. 2,
It's 3 pi over 4. 4 over 4 would be the flat line. Did we want to go all the way to the flat line? No, so we have to go one less, so it's 3 pi over 4. Now, here's the problem. This is not completed yet, because this problem specifically said we want all values of theta. The word all and the fact that there's no domain restriction saying between 0 and 2 pi means we have to write a general solution here. The all is your hint for that. So when we write the general solution to these equations, we would say theta would be equal to pi over 4 plus 2 pi k, and theta is equal to 3 pi over 4 plus every revolution after that, given that k is an integer. It just is like a placeholder for like us to put the number 1 or 2 or 3 in there, saying there's either 1 revolution of the circle, 2 revolutions of the circle, 3 revolutions of the circle. This is how you answer this question. Again, specifically because it wanted all the solutions with no domain restriction, you have to give me the general solution, otherwise it's not done. Do we see the difference there? So if we walk back through the steps, we used some algebra skills to solve and get the isolated trig function. We used our unit circle knowledge to figure out what angles give us square root 2 over 2 for sine. And then we used the domain restriction, which there wasn't one, to write the general solution. Can we try another one? Yeah. Example 2 is a little bit longer in the words, but it's not a different kind of problem. It says, let f of x be equal to 3 plus 2 cosine of x, and g of x equal to 2. In the xy plane, what are the x coordinates of the point of intersections of the graph of f and g for 0 is less than or equal to theta, which is less than 2 pi. This is nice. Do you see this right here, having a restriction on where we can answer for theta? This means we are not writing a general solution anymore. We're just going to be able to give the 1 or 2, maybe 3 or 4 angles that will answer this question. Now, what is the actual question? It asks me for the intersection of f and g. What does it mean for two graphs to have an intersection point? Where they cross, where they're equal, yes? So if we take this function and we say, all right, we want to know where f of x will be exactly the same as g of x, meaning that they'll cross. The f of x function is represented by the equation 3 plus 2 cosine of x, and the g of x function is represented by the constant 2. We see how I'm just plugging them in? It now looks like the kind of question we had in example 1, where it's just a simple solving trig equation. Our first goal was to get the trig function by itself. We need to get rid of the 2, but before we do that, what else should we get rid of? How do I get rid of this 3? Subtract it from both sides. So if I subtract 3 from both sides, those are like terms, so I can cancel them out. This becomes 2 cosine of x equal to negative 1, because 2 minus 3 is negative 1. What should be my next step? Divide by 2. Okay, negative 1 divided by 2, I can do that. That's just negative 1/2. So my question becomes, cosine of our angle, and I guess I should have been using theta this whole time. In fact, let's make this better. Let's just change this theta to an x up here so that I'm using the same variable the whole time. That's my bad. But if I have cosine of x equal to negative 1/2, what are the angles in my unit circle that would give me negative 1/2 for cosine? So remember, cosine is the above fingers. So on the hand trick, which finger are you putting down for one finger to be above? Your pointer finger, which is the which angle? Pi over 3. Now, we want this to be negative, so can we answer with pi over 3? No, we need the cosine values to be negative 1/2, which means we want this in quadrants 2 and quadrant 3. Cosine will be equal to negative 1/2 at the x value of 2 pi over 3, which is the quadrant 2 version of that angle, and 4 pi over 3, which is the quadrant 3 version of that angle. Now for this problem, we are actually done once we have these two values, because we didn't want to write the general equation. We had this domain restriction to begin with. We can only give angles in one rotation of the circle, which is just your regular unit circle, nothing extra. Questions, comments, concerns? Where am I losing you? Let's try the third one here. It says the function j is given by j of x equal to 3 tangent of x. Solve j of x equal to square root 3 for all values of x in the domain of j. Okay. Is this one that I'm going to have to write a general solution for? Yes. What was the key word we were looking for there? All values. And it didn't have something that looked like what we were given in example 2, which is like boundaries. This has no boundaries. So we are going to have to write a general equation here. Do not panic though. It says we are going to take j of x and equal it to square root 3. So I'm going to take the j of x function, 3 tangent of x, and equal it to square root 3. How do I start this problem? What should I do next? Divide by 3. I can't do square root 3 divided by 3, so I'm just going to leave it exactly like that. But hopefully your spidey senses are going off that we recognize that fraction as one of our special fractions. Yes. What angle makes tangent equal to square root 3 over 3? Pi over 6. Very good. Is that the only one? No. What's the other angle that makes tangent equal to positive pi over 6?
5 pi over 6.
That'll be in quadrant 2. Give me the that'd be quadrant 4.
7 pi over 6.
7 pi over 6. You guys, we're getting there. We're getting there. Okay, here's the deal though. These are the answers in one revolution of the circle. But this question wants all values of x in the domain of j, which means this is one of the ones where we have to write the general equation where we do pi over 6 plus pi times k, given k is an integer. Now, fun fact, I only have to write one of these. Even though you guys found two answers in one revolution of the circle here, I only have to write one general equation. Can anybody tell me why? It's only pi, it's not 2 pi. And my question for you is, if I was writing the number pi with a denominator of 6, it would be 6 over 6 pi, right? Because 6 over 6 cancels and it would just be pi. What's 1 pi over 6 plus 6 pi over 6? Isn't it already 7 pi over 6? So we don't have to list both of them out because having a period with the length of pi gets us to all of our solutions of tangent anyways because of its domain. Or sorry, because of its period. Questions, comments, concerns before I make them harder? We're following along. We're isolating. We're thinking about a unit circle. We're thinking about domain restrictions. Here's one of the ways it can get harder. If we start talking about higher order polynomials, we have to start understanding the notation that is used with trig functions to talk about squaring these trig functions. So it could be very confusing trying to square a trig function when it's written like this. Sine of x squared, because if you forget those parentheses, then it's sine of x squared, and you're like, are you squaring the x or are you squaring the sine? So instead, for any higher order trig function, we put the square behind the letters, but we really mean that entire function has been squared. We just drop the parentheses and put the square behind the sine instead of the x. Accepted? Great. The problems do not change. I'm still going to ask you to solve for the zeros, find the solutions. What are the x-intercepts? Those are all the same. It's just that now we might have a higher order polynomial to deal with, higher order trig function, to deal with. This question number 4 says the function g is given by g of x equal to 3 minus 4 sine squared of x. What are the zeros of g on the interval from 0 to 2 pi? Will I need to write a general equation for this one? No, because this is my domain restriction. It only wants one revolution of the circle. You don't have to keep going, so we don't need a general equation here. When it says what are the zeros, zeros means I'm setting the equation equal to 0 and solving. Like the zeros of a quadratic, you set it equal to 0. We're doing the same thing here. So we will do 3 minus 4 sine squared of x equal to 0. And we're solving for x. Walk me through this one. What should I do first? I agree. Subtract 3 from both sides. This becomes negative 4 sine squared of x equal to negative 3. What next? Divide by negative 4. The negative 4's on the left side will cancel, and on the right side, the negatives will both cancel, but I get 3 over 4. The sign is not isolated yet because the sign is squared. How do you get rid of squares? Square root. Okay, bonus question on this. When I'm square rooting something, what do I also have to put in front of that square root? Plus or minus. Nice. So when I'm going to do this one and I'm square rooting both sides, this becomes sine of x equal to plus or minus the square root of 3 over 4. Now, before you start thinking, that's so scary and gross, when you're taking the square root of a fraction, you can do the top and the bottom separately. Meaning, I am really doing plus or minus square root 3 over square root 4. Can you do the square root of 3? Can you do the square root of 4? Yeah, what is that? So we're really trying to ask ourselves, what are the values of x? That when I plug it into sine, it gives me either the positive or the negative version of square root 3 over 2. Sine is the below finger, so what finger do I put down to have 3 fingers below? Pi over 3. I want every version of pi over 3 around the circle because I want both the positives and the negatives. So the solutions to this equation are x equal to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. I don't keep going because it only wants the solutions in one revolution of the circle between 0 and 2 pi. But I have 4 solutions because I want both the positive and both the negative angles that give me, or Both the angles that give me the positive and both the angles that give me the negative, you know what I mean? Okay, pause. Let's talk about this one before we move on. Please ask me some questions before we go. Yeah, great question. Actually, this is just a typo. Look at the letter I'm using in the formula. So this should have the same letter. It's not that I'm marking it out like don't use this. It just should be an X, or these should be thetas. That's just my bad. That's just a typo. In fact, we won't have to do it. Oh, nope, we will. I messed that one up too. Never mind. Can we try number 5? Okay. It says, what are all values of theta where cosine squared of theta is equal to negative cosine of theta? First things first, am I going to need to write a general equation here? Yes, because what was the key word? All. And I didn't have any boundaries. We're good to go. We know we're going to have to write that general equation. The question here is starting to solve cosine squared of theta equal to negative cosine of theta. Remember, theta is like an x. You can't just switch it to an x because that's not what the problem is using. The problem is asking you for theta, specifically an angle, not a variable x, so leave it as theta. But I see already that this is a squared term, and my spidey senses from when I took algebra or the fall of this class with polynomials is telling me that I should put everything on the same side of the equation to set it equal to 0. So what I'm going to do is I'm going to add cosine of theta onto both sides. Now, cosine squared of theta and cosine of theta are not the same, so you cannot combine them. This becomes cosine squared of theta plus cosine of theta equal to 0. I just picked up the negative cosine, dropped it on the other side. Here's where a lot of students get mistaken. Do you notice that both the first term and the second term have cosine on them? Cosine is my GCF. So what I'm going to do is I'm going to take my GCF out of the two terms and put it in front of the parentheses, meaning I'm going to factor out cosine of theta and have my leftovers of cosine of theta plus 1 in the parentheses. Whoa, what just happened? Let me slow down. Again, this term has a cosine in it. In fact, it has two of them multiplied together. This term has a cosine in it. I'm just going to take the cosines, pick them up and put them in the front right here. Inside the parentheses is a leftover. Cosine squared divided by cosine is just one cosine left. Cosine over cosine cancels out to 1. It's like factoring. And when we studied quadratics, and the reason we spend time on quadratics really to get to pre-cal, is that we want to then take both of these factors, the cosine of theta and the cosine of theta plus 1, and set them both equal to 0. Because now I can solve the two tiny equations I have left that separated, like factoring, separated to two little equations, I can solve them. First one's ready to be solved right away. We can think about our unit circle for the two angles that would make cosine equal to 0. We want no fingers above. What angle is this? Pi over 2. So we have two angles. We have pi over 2 and 3 pi over 2, where cosine would be equal to 0. If we solve this one so cosine is by itself, I'm going to have to subtract 1 on both sides before I get cosine of theta equal to negative 1. Where is cosine of theta equal to negative 1? The angle that makes cosine equal to negative 1 is pi. So I have three numbers, three angles that I am saying would solve this equation. 1, 2, 3. I need three general equations to finish this problem. The three general equations would be as follows. This is cosine, so its period is 2 pi. We'd say pi over 2 plus 2 pi k. We'd say 3 pi over 2 plus every revolution after that. And we'd say pi plus 2 pi k. And every revolution after that, given k is an integer. Questions, comments, concerns about maybe these two before we get going? If the part is still just getting the unit circle down, I accept. We will continue to work on knowing these values quickly. But the solving part is really what's new today. Are we doing it? Yes. Are we doing okay on the solving part?
Yeah.
Okay. Example number 5. It says, and also this is probably actually number 6. It says 6. You're right. Let f of x be equal to 2 sine squared of x and g of x be equal to square root 3 sine of x. In the xy plane, what are the x coordinates of the points of intersection of the graph in f and g for 0 less than or equal to, again, that should say x and not theta. That's just a typo, my bad. Between 0 and 2 pi. Now you guys answered this earlier. What does it mean for two graphs to intersect? Where they cross, they're equal. So what we're going to do is kind of like the front page. We're going to say, all right, we want to know where f of x will be the same as g of x, or will cross g of x. So then I can substitute their equations in. This is going to be 2 sine squared of x equal to square root 3 sine of x. I see, again, that I have something that's squared. So I have to let my brain think back to when we learned about quadratics. And when we learned about quadratics, which are squared, we always want to set them equal to 0 if possible so that we can factor and solve. So what I'm going to do on both sides is I'm going to subtract square root 3 sine of x to move it onto the side of the equation with the squared sine term. Again, these are not like terms, so you can't combine them in any way. You will just write them next to each other. 2 sine squared of x minus square root 3 sine of x equal to 0. Is anybody's spidey senses going off here?
Nope.
We have a GCF. What do both of those terms have in them? Sine. We're going to take the sine out. We're going to put it in the front. We are factoring out just 1 sine of x. If I take out one of the sine of x's, the first term turns into 2 sine of x. If I take out the sine of x from the second term, what's left?
X.
Wait,
Sine.
If I take out the sine of x, what's left?
Square root of 3.
The square root 3. Okay. Once I have a term factored, something times something equals 0, the zero product property of quadratics and equations in general tells me that I can separate these into two equations. I have sine of x equals 0, and I have the stuff in the parentheses equal to 0. For the first little equation we wrote, the trig function is isolated, which means we go straight to the unit circle. What are the angles that make sine equal to 0? I want no fingers below. What angle is that? Yes, but go backwards. I want a smaller angle than that. He said 2 pi. What else is at the same place as 2 pi? 0. I want 0 for one of them. Now there is another place where, besides 2 pi, because you're not wrong, where sine would be equal to 0. It'll be pi. It's the other direction. Nice. Now, we won't include 2 pi specifically because this domain restriction says that we actually can't. But you were thinking in the right spot. We have to go from bigger, 0, greater than or equal to 0, but not all the way to 2 pi. Like just underneath 2 pi. So I have 2 of the solutions. Let's go. I just need to find the other ones. Because now I have the other tiny equation that I need to solve. But luckily, solving this is not that hard. Just like old school algebra, we're going to isolate the trig function by adding square root 3 to both sides. What would I do next? Divide by 2. I have sine of x equals square root 3 over 2. And then since the trig function is isolated, we can think about our unit circle. What finger do you have to put down so that we're looking at square root 3 over 2 for sine?
over 2.
Ooh, below, because sine is below. Square, or pi over 3, right? So I know one of the solutions is pi over 3. I just want that angle in quadrant 2 since this is a sine. And sine is positive in quadrant 1 and quadrant 2. What's the version of that angle in quadrant 2? 2 pi over 3. So I have 4 solutions here. I don't have to write a general solution for all 4 because I had a domain restriction. You can just tell me 0 and pi, pi over 3, and 2 pi over 3. Those are the solutions to this equation. Pause for a second, look back through this problem from start to finish. If there's a time and a number showed up somewhere and you're like, no idea where that came from, now's the time to ask. So we don't just have to be able to solve regular trig functions. We do also have to solve inverse trig equations. So here are the steps for you to solve inverse trigonometric equations. Step 1 looks very similar. You're going to isolate the inverse trig function on one side of the equation, just like we did with regular trig. Then we're going to use inverse operations to create an equation with only regular trig functions in it. The non-inverse, if you will. Then you're going to evaluate the trig ratio using the unit circle, and then if there's any algebraic skills needed to solve after that, you will see an example of that, you will solve for x. Yes? Wait, there's a pass. Number 7. The function g is given by g of x equal to 2 times the arc cosine of x. Solve g of x equal to pi for values of x in the domain of g. Notice that there's no domain restrictions in this problem the way they looked before, but we already know that inverse trig has domain restrictions. Arc cosine is only available in quadrants 1 and 2. So we hope that we find an answer in quadrants 1 or 2, otherwise we say no solution. Here's how we do this one. We're going to set g of x equal to pi, meaning I'm going to set up 2 times the arc cosine. I didn't put enough c's in that equation. The arc cosine of x equal to pi. Now, a couple people have asked me this. What is arc cosine? Remember, that's the same as inverse cosine. There's 2 ways you can write both of them, either arc cosine or inverse cosine. So cosine to the -1. But we want to isolate the inverse trig function. So what do I have to divide both sides by to make that happen? Divide by 2. Okay, so we divide by 2, divide by 2. I'm left with just arc cosine equal to pi over 2. The next step says to use inverse operations to create an equation with regular trig. So I'm basically going to remove the arc and the cosine part of this function and move it to the other side of the equation by changing it into regular cosine. It basically breaks out or lets this x that was inside the arc cosine go. I'm now able to access this x that I wasn't able to before because it was in this function. So if it's arc cosine on one side, it's regular cosine on the other. And now this is a question from your unit circle. This would have been on a quiz trade card that I've been asking you for a long time. What is cosine of 1 pi over 2? How many fingers above that? 0. The solution here is 0. So we want to isolate the inverse trig, make it a regular trig question, and answer it like we've always done. It sounds scary when you look at the fact that there's 2, like arc cosine, you're like, I don't know what to do. Don't panic. We can do it in ways that we know how to evaluate functions. Can we try another one immediately? We do have to, but I wanted to make sure if there were questions. Azariah? The function h is given by h of x equal to 18 times inverse tangent of square root 3x. Solve h of x equal to 6x for all values of x in the domain of h. Again, it says all, so our brains were like, general equations, but not for inverse trig. There's already domain restrictions because it's inverse trigonometry. Tangent can only be used in quadrant 1 and quadrant 4, but only through negative angles. So we know there's already domain restrictions there. Let's solve. So we set 18 times inverse tangent of square root 3x. We set that equal to 6 pi. We're trying to isolate the tangent first, the inverse tangent. What do I do on both sides? Divide by 18. I'm going to divide and reduce at the same time. So this becomes inverse tangent of square root 3x. 6 pi over 18. I need to do 6 over 18, and I don't have a calculator to do it. 1 over 3. So this becomes pi over 3. 6 goes into 6 once. 6 goes into 18 3 times. 1 over 3. Once the inverse tangent is isolated, we're going to take off the inverse tangent, break away that parentheses, move the tangent to the other side so that this becomes square root of 3x equals to the tangent of pi over 3. Do we see this now? This one's almost maybe a better example because the square root 3x was tucked inside of tangent. To get it out, I had to get rid of this by throwing it to the other side and making it regular tangent. Does that make sense? Okay, what is tangent of pi over 3?
I know it's something pi over 6.
No. I know why you said that, but no. It starts with a square root.
What?
We're doing tangent of pi over 3. So this is pi over 3, ring fingers down. Sorry, pointer fingers down. How many fingers below?
3.
How many fingers above?
1.
Square root of 3 over 1.
Oh, I said 1 over 3.
Which is just square root 3. I know we're thinking correctly. We just didn't quite get there. That's okay. So tangent of pi over 3 is square root 3. Last time we did one of these problems, we were done right away. But there's some algebra we need to take care of because the x is still not isolated. Well, I've got this giant square root going on. How do I get rid of that? Square both sides. That means 3x is going to be equal to 3. Square root of 3x squared is just 3x. And square root of 3 squared is just 3. What's the last thing here? Now I can divide by 3. I get x equal to 1. Nice. Same kind of question. 7 and 8 were the same kind of question. We still just isolated the trig function. We still just read our unit circle, quote unquote. It just took us a little bit of solving after that to finish solving for x. Last one. Number 9. The function g is given by g of x equal to inverse sine of x over 5. Solve g of x equal to negative pi over 6 for all values of x in the domain of g. Again, I don't need a general equation because inverse sine already has domain restrictions. But I can go ahead and set this up. I'm going to say inverse sine of x over 5 should be equal to negative pi over 6. Do I have any work in the isolation step? Or is the inverse trig function already isolated? This is by itself, right? There's nothing multiplied in front or added behind. We're isolated. So I changed this equation using inverse operations to write it now as regular trig. So here I have x over 5.
We multiply that?
Hmm?
Would we multiply that?
Eventually, yes. Let's do the unit circle moment first before we multiply it by 5 to get the x isolated. But yes, we will be doing that. So we need to know what is the value when I plug in negative pi over 6 into sine. Which is kind of an advanced question. Negative pi over 6 will be in what quadrant? Why is it in quadrant 4? And negative means we go what direction? Clockwise. Yes, down. Clockwise. So if we're just going down a little bit, we're in quadrant 4. Is sine going to be positive or negative in that quadrant? Negative. But sine of pi over 6 is 1/2, so this is just negative 1/2 because it's in quadrant 4. So I have x over 5 equal to negative 1 over 2. Jasmine's idea is correct. We are going to multiply both sides by 5 because when we multiply by 5 on both sides, The 5s are going to cancel in the top and bottom on the left side. And the only fraction I have left at this point is -5/2. And that's my solution.